Hello, everybody, and welcome to another episode of the JUXTCast. I'm Malcolm Sparks,
I'm Jeremy Taylor.
And I'm András Gerlits.
and we had András on as a guest on our previous episode on Horizon, which you can look back at. So András joined us about the Horizon IT scandal earlier on this year. But today we wanted to talk about consistency and distribution and things like that. So András, can you give a bit of an introduction to yourself? How did you get into the industry?
I've been overwhelmingly working as an integration specialist. So I spent pretty much all my professional career in banking, of which I've spent almost 10 years in the city of London as a contractor, as a freelance contractor back before the IR35 changes came in. And there were a lot more of us. So I saw a lot of projects, and I saw I saw I saw how problematic the data was between those projects, and how much most of the times when we had problems. I think I once did a mental calculation of this, but I can't remember more than a handful of times when code that we wrote went wrong in production. But on the other hand, I just can't count the number of times that data went wrong in production. So some kind of a data synchronization issue. And I desperately wanted to change that. I thought I wanted to build a startup. I felt that the time was right about 10 years ago. And this was the problem that I identified as the biggest problem that I can think of, which is uh, distributed data all across the world safely, and meeting the compliance obligations of banks and all the auditing requirements of banks altogether. And this seemed like a nice compact little problem to have.
So let's go through the issues with data synchronization. Why has it become such a thorny issue today?
Well, I think there are two main reasons. One is the horizontal, and the other is the vertical, which is jargony ways of saying that we have data in more places, both geographically and in different services, throughout different services, and those different services do not necessarily play nice with each other. And geographically, um, like even today, um, network connections are much better than they were 10 or 15 or 20 years ago, but they still can be choppy given a long enough network. We still get more variance in its quality, which has a big impact on the predictability of the flow of information from one place to another. This is the basic problem. There have been a lot of formalizing around it. There's been a lot of you can call it math if you like, put around it. But the gist of the problem is the further away computers are from each other, the harder they find to communicate with each other. That's essentially it.
And data synchronization is important because we make decisions on data. And so if we have discrepancies and if our computers don't agree about what the truth is, then we can potentially make wrong decisions. And data is very spread out these days. I know that um, many companies work on spreadsheets and they're built on spreadsheets. And spreadsheets are, in a sense, a little database that you have that is, a snapshot of the truth, but it can become stale very quickly. And I think anyone who's kind of used spreadsheets at scale where you're kind of trying to kind of all agree on a single truth, you'd probably have as for anyone who's got a spreadsheet, there's that many different versions of the truth. So, how do we begin to address this problem of synchronizing data? What's the traditional approach to doing it?
What people used to do was batch files, like big batch files, usually overnight batches, whatever overnight meant in terms of. We had this beautiful saying called "follow the sun," whatever that meant. I never fully understood what it means, but that's what it meant. That's what they said. Um, so it used to be overnight batches, which have been improved somewhat, and I see a lot of change data capture nowadays it's called. So the idea is that you take some information and then observe the information as it's being born, and then formulate little events from that and send over those events over the wire, right? And then you somehow make sure that those events actually end up in the destination via some kind of a checking mechanism. That usually gets fairly complicated fairly quickly.
Well, even before that, we had, when I was doing computer science at school, we were taught that every company had a master file of accounts or transactions or something, and every time you wanted to change that master file, instead you wouldn't change it, you would add to a transaction file that would you would just post your hoped for change, and then overnight the tapes would wheel around and the master file would be updated, and that with that batch, that would be the overnight batch, and then in the morning the master file would have the new balances or the problem was, of course, like when you look at your balance in your bank account, it's not today's, oh, it might be last night's balance, but it doesn't incorporate all of the changes you made today. So um, that was the big trade-off. But we wanted to have much more real-time, up-to-date information. So what do you think? How do you think we what are the steps that went from that kind of mainframe processing in the center of an organization? How did things begin to decentralize?
I remember, like, I was lucky enough to live that, to to actually experience that era, because my mom was a software engineer. She's now retired, and I grew up between those mainframes. But even back then, even in the Eastern Bloc where I grew up in Budapest, we had interconnections between these big mainframes, and we were early with the dial-ups and everything. So even our home computer contributed data to other systems. Even like there were these really slow 2400 baud modems. So anyway, that was already some form of interconnection between these systems. And as soon as you have multiple connections with them, you have multiple processes running in parallel, and they all want to contribute something to the system, or else what are they doing here, right? So they either want to look at something or write something, or both. And from that, so back in the 60s, when Dijkstra came up with the idea of a semaphore, which arranges these little processes into conducts these processes into a nice tight order, where they give exclusive access to certain chunks of information to processes, and that has been extended, where rethought, I think is the better word, in the 80s, mostly by Jim Gray et al. I think he worked together with Lamport. And so that they formalized what had eventually become the ACID requirements, which is an abbreviation for, I think it's a backronym, I'm fairly sure, but it's atomicity, consistency, isolation, and durability. And I don't think we need to go into the definition of each word here, but that's what it stands for. The idea is that you can compose these processes into a safe platform, where you can expect certain things from the data on that platform that you read, and you can have certain expectations towards the safety of you writing that information.
Yeah, when I started my career, ACID was the sort of kind of people were talking about. Jeremy, when was the first time you were at IBM? When was this kind of first time you remember hearing about this acronym ACID, and what do you remember it meaning? What did it mean to you?
I couldn't tell you the very first time. So my interest in databases did begin when I joined IBM, and it was actually exposure to Lotus Notes. So this was probably 25 years after Lotus Notes first came out, 2010. I get handed a company laptop, and it has Lotus Notes installed as the email client. But at that point, I had no idea about the legacy of Lotus Notes being this essentially a distributed database versioning, message passing sort of platform, which is interesting in itself. But yeah, around that same sort of time, I got quite interested in databases, and I think MongoDB was still very much on its upward VC-backed hype curve, and probably still losing people's data at that point. And yeah, Acid was a big part of that scale out sales pitch, because we're serious databases, just like the traditional relational databases, but they don't have referential integrity, etc. But they do have Acid, so that was the first exposure I guess I had to the concept. But yeah, certainly there's a much longer history in exactly how it's defined and what it means that I think I'm still coming to terms with, and I haven't gone through all of Jim Gray's old papers from the 80s. So
it's funny you mention Lotus Notes, because that really was, when I started my career, that was kind of a sort of peer-to-peer system. In fact, there would be multiple, I think, database replication, and I think it was maybe master-to-master replication. I don't quite know how it worked, but it was a little bit of an outlier, because for the most part, when we were building networks of PCs and networking them, that we were networking them in order for them to talk to a Unix server, which was running a single database. And it was only a few years later into my career that we started whispering about replication, that you would have data in one database and you would need it maybe in a different geographical location. So we began to sort of talk in hushed tones about snapshot replication and master to master replication, which is where you could have two master databases sort of synchronizing. But I always got burned by this, and we was told never do this because it's just full of problems. So we're beginning now to kind of understand how, when people started using databases, well, I suppose when databases became commodities and people could you would put your database at the heart of your Ruby on Rails system or your J2EE system, and you'd have many of those systems all networked together. As we begin to see the modern era of multiple databases. Would you agree, András? When was it for you to see these multiple databases?
I worked, like I said, I was by some freak of nature. I don't know how, but I ended up becoming an integration expert early on. So my first project was maybe late 90s, something like that. So we did a lot of integration, and each of them, like, normally the way we started is by we had workflows, and then the workflow orchestrated everything and said step 1, step 2, step 2, step 3. And sometimes it failed, but not very often. But that was because we had the robustness of the system was somehow still. It's strange how early on the computers that we had, the mainframes that we had a lot of redundancies. It had a lot of safety features, and then the servers that we started using had the same level of reliability, but they were much smaller, and there were a lot more of them, but they were still incredibly expensive. And then we gradually keep moving towards, and today the cloud providers specifically provide you a non-commercial grade computer, and they're open about this. They say, well, yes, it's entirely possible for you to lose a VM from time to time, and you just have to live with that, because that's how we can get to be so cheap and so commoditized. So it was a 50-60 year movement from like incredibly robust and safe and reliable computers all the way to everyone running on essentially Raspberry Pis and these throwaway computers. And this would be fine, in my view. It's absolutely fine. I fully agree with the concept of throwaway computing, if our data management would have kept up, if the stringency of our data management would have kept up with the pace of the changes here. That's where I have my difference with with the status quo. Let me put it that way.
So we've we've got a world now with thousands and thousands of different nodes, systems with thousands of different nodes, and we've always said in Juxt, it's not really the distribution that is the problem; it's the distributed state that is the problem. That is where that is where all the problems come in. With the microservices sort of revolution, you just hear so often that microservices is the thing to build. If you're not microservices, you're doing it wrong. And so we're seeing a great movement of the industry to distributed, not just distributed services, but each service in the most common patterns of microservices have their own state, and so and private state. And so when those services, when the company wants to work out what is the truth, well, the truth has been scattered across the organization, so it's no longer easy to join it. And so you have those challenges, but you also have the challenges that there is no longer a single truth, and that truth is kind of changing, but it's changing in different places. So it wouldn't even be possible to suddenly do a snapshot of all, because everything is all moving. You've got kind of space-time relativity aspects creeping in.
There are two big problems with data management in distributed systems, broadly speaking. Of course, there are a lot more, but these are the two biggest ones, and everything else is a product of these. One is the inherently unstable computing and network that we have. We all know that it can blow at any time, and I've seen that happen multiple times at work. And the other is the lack of. It's a lot more philosophical, the second one, but it's the what we when we're trying to sound very clever, we say semantics, shared semantics. So the meaning of what the data means, and the precise understanding of what the data means, not just in the here and now, because there's no here and now. There's always a timeline, but over a time, a period of time, how can it change? What does a change mean? What does it actually mean? Is there a guarantee that the data that I'm looking at now is the data that everyone else is looking at? What about when I compare these two events? Can I be absolutely sure that these two events I know the order of, because they might mean entirely different things? So, for example, transfer money from my account, freeze my bank card, and freeze the bank card, transfer money from my account. They might have very good reasons for either of them, right? Because I might have lost my card, so I want to freeze it, and someone's racing me to transfer money off of that because they just got a hold of it. So what is the truth? What if one system understands it as freeze bank account, transfer money, and the other one understands it as transfer money, freeze bank account? They reach entirely different conclusions about what needs to be done.
Mm.
So,
well, I see it more as that the state of an organization is a function of all of the individual changes, because these problems only are problems to us because the state actually is subject to change. If the state remained the same, if it was just a library book on the shelf and never changed, you can take many copies of a library book, distribute them around the world, it's still the same library book. So that's a solved problem. What isn't a solved problem is when you have multiple authors of that library book, all competing to write words. And I like to think about it as as long as we know the orders of all the words of those writers, we can arrive at the same truth, the same book. It's like having let's say we were going on a walk and we came to a fork in the road and we rolled a dice and we got a 2, and then we went left and then we rolled a dice again. And if we recorded, if we were able to have a dice that gave exactly the same turns each time, we could go on that path and we'd all arrive at the same destination. But you take one dice roll out of sync, and then we can be completely drift off and go into a completely different destination. And so it's kind of an insight. I think we find it very obvious that it's a function or a reduction over all the changes. If you've got all of the changes you want to make to your state and you do them all in order, then you can independently do those steps in any way you like, and you'd arrive at the same state, if you shuffle a Rubik's cube in exactly the same way, and we all do it, we're going to arrive at exactly the same Rubik's cube. One little turn out of sync, if we miss a step, then the Rubik's cube is going to look completely different. So I think that does need to be emphasized, because I don't think it's truly obvious to everybody that you can do this. If you have a transaction log, and that log is in the right order, it doesn't quite matter when the events happen. They don't have to happen all at the same time. But if you can preserve the order, then you'll arrive at the same destination. And I think that's kind of I suppose, a truism. It's obvious to us who've been dealing with logs of events, but I think it's worth kind of pointing out that this is a very useful trick, and this is why we talk about events so much.
The other thing is, we're not the only ones making decisions about the data. So, for example, we touched upon semaphores earlier, and semaphores, for example, which are sitting in the middle of the computer, they are deep down in our OS, and they do something called race conditions. So, when there are two processes who are both competing to update the same piece of information, then the computer will arbitrarily choose between one of the processes. There's no guarantee on which one it will choose. So that's original information being created in the system, because that information needs to be controlled for if you want to be able to shuffle the Rubik's cube as if you were, right? So there are a lot of, or even looking at a clock. Looking at the clock of a computer, it seems very intuitive that we need to order by the clock, but the clock is also a source of ambiguity, because we don't know what the clock says, and the clock will say different things on different computers when we're trying to replay these sequence of events. So yes, determinism can be used for reconstructing the same understanding of the data, but you have to be extremely careful in how you manage that.
You have to create a closed system.
You have to create
absolutely sure.
You have to create a closed system, and you have to test for that closedness of that system.
But that's what a database is.
Absolutely.
Surely a database is that closed system that you can provide, and you can say, right, now you can just give me a number of events which we call transactions. But if you give me those, they kind of, there's a kind of gateway into the database saying that you can only change me if you go through this SQL language, or make these transactions. Should we just touch upon the kind of what transactions are? As you know, they are tied to events, but what do we mean by the word transaction?
Well, I think the most obvious definition, the clearest definition that I can think of without too much jargon, is that it's a collection of operations. I suppose it's a sequenced collection of operations issued by a specific process. Now, this has come across a lot more jargony than I wanted it to, but I tried to be precise. So
I like that. Yeah. The sequence of operations. Jeremy, would you define it the same way, or how would you think of a transaction?
Yeah, so I guess the ACID definition, maybe we do have to dive into each one of those letters to understand the full meaning. I think the most important one is the atomicity. So when you have this sequence of operations, you just want to say they all apply or none of them apply. The others may be nice to have, but I think that's the first property you want from a transaction. And then the others would be sort of, can transactions observe each other's effects? Because otherwise it gets very confusing if transactions can observe each other's effects. So you want isolation between them. And if you're building a real database to store serious data, you would like to know it's actually stored. So that's the durability. And then consistency is probably the hardest one to talk about, ironically.
There's a joke that which is two programmers, three definitions for consistency. And for very good reasons, actually. It's just because it's the expectation of the client of the system, of the user of the system. That's what it is. That's all it is. We have a model of it. We have different models of it, but at the end of the day, it's whether this system works as expected from the client's perspective. That's all it is.
No surprises. That's the happy part, isn't it?
That's a very good definition.
Yeah, I was thinking, talking about this, the encapsulation of the database, protects you from these consistency problems. It reminds me of a very similar set of constraints and circumstances that's happening way down deep in the bowels of the CPU, where you have a clock, which is sort of allowing all these logic gates to coordinate, and the chips are massive, so massive that by the time some set of instructions has gone from one side of the chip to the other, the physical clock time on the chip is gone forwards several nanoseconds, which is enough time for the speed of light to move half a meter or whatever, and the whole chip needs to be synchronized such that by the end of the next clock cycle, all the logic gates have done their processing and everything's on the bus, or the next registers that needs to be there, and data's moved onto the bus, whatever. So I almost see like the CPU as just a tiny little database with huge numbers of nines of reliability, because it's like perfectly well tested, and they do a lot of testing of chips before they send them out of the factory. Anyway, just a small aside, but
I'm completely with you on that. I think the CPU is also a collection of processes competing with each other for being to be the next process that provides the next value of a set of information. So I completely agree with you. And there's a good reason that people have been pushing towards transactional memory, so that we can go down and do those things down in the bowels of the computer itself, not just for the macro. But actually quite funny that the big, well, I know it's a tautology, but it's an oxymoron, the big macro. So the mid macro works well, which is regional databases nowadays seem to work. Global databases don't seem to work that well. So there's a sweet spot for databases which have grown quite a lot in the last 15 years, which is nowadays something like what the cloud providers specify as a region. And it used to be a single computer, then it used to be a small cluster of computers, and now it's like something like London or Frankfurt, right? But we still don't do that well with a globally distributed consistency, right?
So I love the definition that consistency is just whatever makes sense to the user. And it reminds me of, if I'm reading I have a 5-year-old daughter, and I'm reading her stories for bedtime. And if I was to read a story like Cinderella and say, well, Cinderella was this, she was, getting ready for the ball. And then, she went outside and saw a lovely kind of, coach and horses. And then the fairy godmother turned up. My daughter was, no, the fairy godmother has to come first in the story, because the fairy godmother has to make the coach and horses, and so from my daughter's point of view, a certain sequence of events would make sense. And if you get those things out of order, it doesn't make sense. It's like we were talking about having a single banana in a fruit bowl, and if I went in, got the banana, and then Jeremy came in and also got the banana, you'd think, well, that doesn't make sense. There's only one banana. And so when we talk about consistency, really, we're just talking about the world making sense from the perspective of a user. Is that right, András? Or rather, because if we get these mad things that go on, like the coach and horses arrive before the godmother, you get all kinds of, well, inconsistencies. You make decisions. How can you make decisions like, well, you've closed the bank account and now you've credited it? I mean, how does that, and then you have to develop all kinds of mistake rectification, coping mechanisms and things to cope with the fact that the world doesn't make sense from the point of view of the observer.
The strength of this definition is also its weakness, though, because it's so flexible, it's so fluid, right? It expects the observer to be the judge. So we say consistency is in the eye of the beholder. Well, that's easy to say, right? Who's the beholder? Where? What sort of requirements do they have? How well can they specify those requirements, right?
But we're getting to something which is a little bit more like we began to talk about events as if you
Absolutely.
did have events in exactly the same order, like in the Rubik's
Yes.
Cube, you're going to end up with exactly the same
Yes,
combination.
which is why the definition of consistency that people usually work with is actually a specific definition. It's called strong consistency definition. And the strong consistency definition is that, and this is very important because we're going to get into the clocks, but it says, and this is important, that all observers agree on the sequence, on the order of any two events when compared with each other. Right? That's a better definition than the one I almost said. But yeah, so any two, you pick any two events at random, and all observers will tell you what that order was. That's the definition of strong consistency. Now, usually people take this to mean, well, there must be a clock somewhere, right? Because then we say, well, happened before, so there must be a clock. And
can I ask a question?
Sure.
Is that intuitively, that sounds like we all agree on the exact order of events, but there's something a bit deeper about causality.
Yes.
So can you just touch on that? Because to my brain, that just sounds like if you can, everybody can agree that given any two events, which order they came, which was the cause of the other, then surely that is the same as saying we almost all agree on the absolute order of the event.
We say that we can establish a causal relationship between all two events in the world. That's what we say. Or there was at least certain kind of causality that happened that somehow interleaved these events into each other. I think I need to explain a bit more here. So you have multiple things in the world. I'm trying to not get too jargony, but this is important, I think. You have multiple sources in the world which emit information. It's a lot like how my lamp works, that it sends information towards me all the time. And you have many of these things emitting information constantly. And this is where the famous cone from Albert Einstein comes in, which is it travels with time. And as these times intercept each other, so it has this opportunity to reach more things as time travels forward, because there's it widens on the area which it could touch. So the same thing happens with computers, actually. If you think about it, that's exactly how computers work. They are original sources of information, many of them, all of them, basically. They emit information towards the others, and then the others get to observe the information that has been emitted by them and react to those, yes. But it's the same as the physical world. There's no hard difference because these are physical objects. So it's just that the rules of physics apply to them the same as us. And most of distributed systems research has been centered around, and this is, again, I'm going to explain everything, something called linearizability. And linearizability says, so the definition of linearizability is that if someone wrote down something somewhere, then a system is only linearizable if all the other observers can look at it immediately. Right? Now there's a weasel word here. And the weasel word is immediately. What do you mean immediately? Whose time? Who says what time it is? Your time is not the same as my time because we're quite far from each other. In fact, that person about 20 meters from me doesn't share the same time as I do, if you look at it on a precise enough scale. And this is important because computers are looking at it at a precise enough scale nowadays. So it's not, it does a sleight of hand. It says it has to be observable by everyone immediately. Well, immediately doesn't mean anything in a distributed system. I think then this is a definition I came up with, but I had to come up with a definition because I wanted to build a software around this concept. So my definition is that immediately can be redefined or should be redefined as the first time that the remote computer had a chance to affect the state of the local computer. Because everything else, so let's say that we have the perfect streaming channel between the two, the perfect network connections, median throughput. When is so what is immediately is the time it would have taken for the remote computer to send that information immediately to the other computer, and then the other computer picking it up as soon as it can. Classic causality. So that's my definition, and I think my definition is, well, at least more precise than the others, because they don't define the world clock. I've never seen a world clock that is perfectly precise. If it exists, I would like to know about it, because I think it violates the rules of physics. So that's how I've built my system. I've built my system around that definition of causality, and the idea that if you have multiple of these events being emitted, then somehow they need to be interleaved into a single order. You can't establish order via some kind of an external authority and expect everything to work. You have to make the participants play nice with each other in interleaving the events that they're emitting, and somehow that interleaving process should be able to navigate upwards on a hierarchy, so that we can have a wider interleaving processes, have increasingly wider interleaving processes above them, so that
is the goal that every node in that network ultimately gets the same interleaving?
Yes, but so this is why what I said about strong consistency definition is so important to be precise about, because strong consistency doesn't say anything about time, right? It says you need to be able to tell the absolute order between any two events, but it doesn't say you have to immediately be able to tell the order between any two events. Now, I think a lot of people presume that means it's an eventually consistent systems, but as my friend and colleague Mark Burgess always says, every system is an eventually consistent system. We just give the time and space for some to catch up with themselves, right? Because we block, so we make the user wait until we know what the answer is, right? And we can do the exact same thing here. We can say, we don't know what the order between these two events is yet, but Margo, listen on this, and once we know, we'll tell you here. So I think the biggest thing holding back data in banking, like it is so far removed from the actual experience on the ground. I get that, right? But so it's a bit absurd on the first sight, but that's the biggest problem. The biggest problem is the concept of shared time. How do we share time between each other? How do we establish that global order that we wanted? As soon as we have that, we can talk about redundancy, we can talk about determinism, we can talk about replication, we can talk about latency mitigation, all sorts of tricks that we couldn't do before.
Why do you think this is, when you say banking?
Yeah.
I guess I could ask, what do we mean by banking? But that would be, what I'm trying to get to is, why do we feel these problems in banking so acutely, and not necessarily in other industries? Or perhaps we should, or we do. What I'm getting at here is, because of the financial system, if I do a trade with another counterparty, it really is quite important that we both have the same understanding of that trade. If I give you, yes, that's right. I mean, the numbers all ultimately have to add up. Hopefully, I was quite shocked when I joined an investment bank to find how kind of fast and loose these numbers are, and and how really consistency is eventual, because it employs armies of manual spreadsheet analysts to kind of patch up all the errors after the event. So ultimately, eventually, through lots of human input, the system is consistent. But we still try to build systems in banks that ultimately have this problem of having to be globally correct and consistent. The financial system wouldn't work otherwise. We'd end up having so many arguments in courts about how much we owed each other that it would basically make a lot of work for lawyers. And so I think these problems are a bit more universal than just problems in banking. It's just that they're keenly felt in the banking industry.
Another example I recently thought of was the energy grid, the electricity grid, right? You have to have, because you need to send electricity, like loads, from one place to another so that you don't overload it. And then so you have to balance it. And that balancing is actual manual in some sense, not necessarily human input, but computers actually have to balance that load by routing it from one place to another, a bit like a train. So that's another example of where global data is incredibly important to be precise and quick and reliable.
Perhaps another example would be, imagine you're running a very large internet search engine, and you're selling advertising space to people from around the world, and you need to be able to keep track accurately of how those adverts performing and charge the person at the right time. And of course, this is what Google does and did, and why they built the Spanner database, is to track this basically their core revenue engine for the business. So it is definitely financially motivated technology, and it is tracking a very large portion of the revenue. So I would be kind of interested, András, like to understand how you see Spanner. And for people that aren't aware of Spanner, it's like a distributed SQL database which famously relies on atomic clocks synchronized with GPS coordinates, so all the data centers of GPS, and it runs contrary to what you're describing. I feel like that might be quite an interesting contrast to draw.
Yes, very much so. I mean, Spanner is the poster child of distributed systems, of the established way to think about distributed systems. And I've heard a lot of people say it's the best possible distributed system that can ever exist. I feel that it's a bit like saying that objects heavier than air will never fly, because it jumps to conclusions about certain things which aren't necessarily true. I refer back to my diatribe about a shared clock. So they brute forced their way to a shared clock. That's essentially what they did. They decided we have enough cesium clocks and satellites to throw at the problem. So they have. And what that means is that they have these special computers in these special data centers, which are trusted to keep the time. All of them are trusted to keep the time. Basically, at the end of the day, what Spanner is not just, so it's not just the atomic clocks. It's not the atomic clocks that make the system work. What makes the system work is the trust between the other computers that everyone is telling the truth. All the other computers are reporting the right times for the comets that happened.
Can I naively just interject and ask, why are atomic clocks used in this system? And I guess it's because every event that is produced, emitted, no matter which node is emitting it, is stamped with a date.
Everyone has to everyone has to agree on the order of the events.
And so when you then emit those events, you can tell which event came before the other by comparing the date stamps.
Yes.
So it's a sort of so if you didn't have an atomic clock, I think we're getting into kind of what would you do if you didn't have it. I mean, that sounds quite a sensible thing to do. If it was a global time, and it's kind of having an atomic clock is a kind of approximation to having a global clock. But if you throw away, let's just suppose that we can't afford an atomic clock in our system, what would we do instead?
I use causality in my system. I say systems need to establish causality. I force the same way they force they force a global clock into existence. They just by throwing enough technology and people at it. I get an ordinal clock. I get an ordinal clock into existence via forcing causality, causal relationship in a hierarchical setup.
I think we might
So
have to just dig a bit more into what does it mean to say I use
I know, it
causality.
sounded very
Like,
esoteric, didn't it? It's a good thing that I explained a bit about before. So I literally send around messages, even when the messages would not be mandated. Just so I establish order by. So there are two things. First of all, there's causal order. So if you updated something, that then you've seen what you were updating, and then you're trying to be the next one providing the version for that update. That's a causal. That's called causal consistency. You're either rejected from update if you're not updating the last version known to the system, whatever that means. Then you're rejected. Your transaction is rejected. That's called optimistic concurrency. But that's not the only thing, because that doesn't mean that only means that the things which are interconnected can be ordered with each other. To do the strong consistency aspect, I force messages around the bus constantly in a loop, and that way I interleave the messages happened on each node. So it's like a collection event where what have you done in the last cycle? This. Okay, so this is interleaved in, this is marked as interleaved. What have you done in the last cycle? Well, this. Okay, so then this is interleaved, and it does this in a loop around the circle. Now,
when you say the circle, there's like a token ring around all
it's
the
a bit
nodes.
like a token ring, but it's done over a consensus group. So it's deterministic. So it's not like the token ring we used to have in Ethernet, where if you disconnected one computer from the network, the whole network fell apart. It's exactly as alive as your messaging system is. So as long
Okay,
as
so
your message, sorry,
it has fault tolerance, as you know. I remember those token ring networks where one PC would be shut off or
it
something.
has better than vanilla fault tolerance. It has the same fault tolerance as the messaging platform that most of the banks already use, which is mostly Kafka or its ilk, one of its compatible things.
So you've
So
got this virtual kind of token ring going round and round
yes,
and round, and then other than if my interleaving is considered to be out of order or something, do I get to you do
there's no
you
such thing.
well,
The reason there's no such thing as your interleaving being out of order is because the order can only be, so you can't ever be, you might not know what the order is, but you can't be out of order. You can miss some time information, because that way, by doing that thing and by getting mutexes, I'm not going to go into details about that. That way we can decouple the time, and well, decouple the time and the order, and that way and collision detection, and that way we can stream the time information along with the data information. And as long as you receive enough of the time information, you can always calculate how far along am I for a particular scope. So I can say locally I'm consistent up until this point. Regionally, I'm consistent until this point, and globally, I'm consistent until this point, right? And then you can always chalk up, based on the amount of information that you received, how far along you are on your path to enlightenment. So how so that we have something, so that way, and by also doing the cyclical collection in a hierarchy, and then also doing an association loop between the two, that way we have something we can agree on. I can say I'm up until this point on the regional level. Where are you? Right? So we can always pass these tokens to each other, and that's a single timestamp, the same way everyone else is. And it's a single timestamp, and I say, look, on the regional level, you need to be this high up in information to be as informed about the things as I was when I did this, make this decision. So that way, all sorts of magical things happen. Like you said, that you shouldn't do master replication, right? We actually do master commits over Kafka using your existing SQL database, and with a very low overhead. Like the overhead is, well, my 10-year-old laptop runs 200 parallel processes of that, and the commit overhead is routinely under 100 milliseconds. So, and I can assure you that it's not a very good computer. So a lot of magic things happen once you decouple these things, because you get rid of the blocking. It becomes an asynchronous non-blocking system in its entirety. And that sounds like magic, but it isn't, because the mutex is not the only way. Mutex does two things, which is what we talked about earlier, that magic thing that decides who gets to do things. It does two things. It does something called collision detection. It knows who wants to update the same thing, and it also establishes order. It doesn't explicitly establish order, but implicitly it does, because it chooses, via the race condition that we talked about earlier, chooses who the next one will be, and that way establishes order, right? And that's a bit wrong in my view, because it meshes up the semantics of it. Like, how do we establish order? Well, we in a classic system, how do we establish order? Well, we partially establish order via mutexes, and then we also establish order via the select. So as they come in, and then the third way that we also establish order is by access to the write ahead log. So there's all these things going into the consistency sausage in a classic database, right? And this is what causes the problems. The consistency sausage is the problem. It needs to be a steak, because we need to understand how it ticks in order to be able to distribute it well. Sorry, that was a long rant.
It's definitely really interesting. I guess just for benefit of listeners, so the system you built is called Omni Ledger, and it's an implementation of the ideas you've been talking about. It's not generally available right now, like but it is released. Is that right? People could try and.
Well, there's a beta of it, and we are looking for people to deploy it. We're looking for partners to do a POC with on it. It's consistent. It works. It does what we say it does, and it's very, very easy to prove it, because I can give you the test case to run it for yourself. And it currently supports MySQL and Postgres, but the only reason it only supports these two is because these are the most popular. If you tell me exactly which database you want me to support, I'll support that. Because the bottleneck to supporting these sort of things, so integrating these sort of things, is just ossified thinking around mutexes and clocks. That's what I ended up finding after 10 long years in this climbing down this rabbit hole. These are big claims, but I have the software for anyone who cares enough to look. So, and I have proof. If you go to omniledger.io, you can watch the demo, which is a previous version. We're just coming out with the new version, which is a lot more flexible than the first one. But the first one demonstrates this principle of master commit already. It demonstrates transactionality. I'm saying big things, but there's no lie there.
And you're focusing on, I mean, this is an on-prem technology.
Absolutely, and that's the most important thing about it. You don't have to move anything anywhere, and you don't need to introduce new infrastructure pieces. The idea is that the software works via the existing SQL databases that you have and the existing Kafka or Red Panda or single store instance that you're running to as a messaging solution between them.
I mean, and technically, it's a kind of implementation using I suppose the commit and rollback kind of.
Yeah, so it essentially piggybacks on the infrastructure mechanisms, on the mechanisms we use to access the database in Java mostly, or it could be adopted to other languages as needed.
And you're kind of piggybacking on the trigger mechanism that most databases
I'm
have.
piggybacking on the trigger mechanism of the database, and I'm piggybacking on the Java mechanism for how it manages the connection to the database, essentially.
Oh, in the Spring Boot, if you're using Spring
Actually,
Boot,
in Spring Boot, you don't have to do anything. You have to import 2 modules, do some modifications to the property file, and you're good. So it's that, and then from that point on, you can use your existing system, and it becomes a master commit system between different databases across your local network. Yes, or your distributed. So, but think about this. Ever since we started using, so in the late 90s, early 2000s, we started using specialist software. So, for example, SAP was one of the first. When we, so these are specialist solutions. These are not, so not like I don't know, I used to work with WebLogic a lot, being WebLogic, which was, so these were, the WebLogic is a building block, and the application servers were a building block, and you get to, it's a blank page, if you will, right? But SAP isn't, right? It's designed to be an enterprise system, right? So once we had more established, more and more specialist software coming in, there needs to be a way for them to talk to each other, and there's currently no way to do that well, except for workflows, and these are also a bit iffy. You do need people to clear up the state between them from time to time. This thing allows you to make sure that if something happened, everyone understands what has happened within the whole system. So each component understands the same thing has happened. You can have your audit table back, for example, which people used to love so much.
Yeah, what attracted me to the when we first got chatting was because I was well aware that the problems in our industry were mostly around distributed state and the difficulties of that, and therefore I I've been talking quite a bit about kind of our own concept in JUX called atomic architecture, which is kind of a sort of a smaller scale kind of articulation of how do we get back to basics, to use an old kind of an idea that you sort of have to understand the real consistency problems of a microservices architecture, and to say, well, actually it's not really the distribution of the services, it's the distribution of the state. And there were some things in the kind of the monolithical database that we had them, and then trying to get people to think about with the re-embracing the benefits of a single database. But it was a very encouraging, because there came into some criticism when I published some of these articles online that of course this is just a a complete idealized, we can no longer go back to the world of the Unix database and the single Oracle database in the middle of the organization. That ship has sailed. That we've got SaaS systems where most organizations have thousands of different sources of data, and so this was a very kind of a fictionalized idea. But it was really encouraging to when I came across your work with Omni Ledger, that actually there are approaches you can do to distribute state, but still remain consistent, still achieve that consistency without kind of. I mean, Spanner is one approach, and it's nice to know that there is such there is work done in different branches of that problem. But to get people to really understand, if you don't have consistency in your systems, you'll have a lot of work to do in all these repair mechanisms and error correcting mechanisms and all the things that we're and it's those error correcting processes that are just a yet another dimension of complexity in our systems. So really, to solve things universally, yes, we need to get back to this kind of glorious single consistency in our data to avoid these data synchronization problems. But it was tremendously interesting to me, and I think in Jeremy and the work we do in JUX, to know that there are these people like you, András, working on things that are very, very interesting concepts, and with practical implementations where you can demonstrate that things can be done with, well, you can almost have your cake and eat it. You can have your microservices, you can have your distributed databases, and yet there are approaches that allow you to reincorporate consistent state. I think that's just a wonderful thing that you've kind of been working.
There's one more thing that should be interesting, in that it has a lot of, because I came from finance and because I remember the problems we had with compliance stuff. This was designed, a lot of the compliance problems that we had, and it has redundancy baked in. It has for example, it commoditizes stuff for DORA. It 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 has the disaster recovery aspects. It so it was specifically designed with the experience. So it wasn't designed for banks, but it was designed with the experience I had, which happened to be banks.
Of course, I mean, a monolithic database does have some extra trade-offs, like it can go down, it's a single supplier, and so for operational resilience, which is what the if I directive of operational resilience act,
Digital Operation Resilience Act,
the
yes.
EU, that really is a sort of a reason why you wouldn't use an atomic architecture, because you've got to show that you're resilient to the failure of any part of your system. And you may need to cross geographical regions, or to be able to be, that kind of disaster recovery capability. You need to prove it. So that really does call for these kind of techniques to allow you to go distributed, but where every node can recapture the order of the events that we talked about before.
No surprises.
Well, very good, András. Thank you so much for that. I thought that was a really interesting conversation, and well, we look forward to. We do want to just mention XD24 on the show. So we have a quadrennial conference in Juxt. We had XD16 and XD20, which sadly we had to cancel. So we haven't had a conference for 8 years, but we are taking a particular fintech special conference, hosting it in Milton Keynes, which is where our Juxt HQ is. So if you are interested in these kind of topics and you're interested in fintech, do get in touch with us. There are some tickets available. It is invite only, I'm afraid, but we do have, because we have limited space, but we still have quite a bit of space left. So do get in touch with us if you would like a ticket, and to meet András, and to have these conversations face to face.